Someone just say in the chat. And if you guys can hear me, just let me know as well. Okay, cool. So welcome to today's tutorial. We'll be covering geometry. And before we start the tutorial, does anyone have any questions regarding NZMO2? I think NZMO2 is next week, I think next Friday. So does anyone have any questions? Feel free to ask. Okay, I'm guessing no one has any questions, so I'm just gonna move on. Okay, so today we'll be covering coordinate geometry. Okay, so what's coordinate geometry? Coordinate geometry is a branch of geometry where points are assigned a coordinate. They'll be looking at coordinate geometry on the Cartesian plane, which is only two-dimensional. Then, using algebraic methods, we can determine relationships between points and the areas they encompass. So, moving on. Oh, does anyone have any questions? Okay, no questions. Alright, this should be pretty familiar, so I'm not going to spend too much time on this topic, but we'll get into doing some questions later on. Okay, so the distance between 2 points is given by this formula. So the shortest distance between 2 points is given by the equation on the left, and in this diagram here, x2 and then y2 due to point B, and then x1 and y1 correspond to point A. So can you guys see why this formula is right? Is true? I'll give you guys 1 minute to think. Okay, if there are no questions, I'll just move on. Well, no, actually, I'll show you guys why this formula is like true. Like if we draw like a vertical line going through A and a horizontal line going through B, just redraw the diagram here. I have point x1, y1, and then point x2, y2. Then this distance here, I have because the vertical line going through point A is perpendicular to the horizontal line going through point B, right? So therefore, there's a right angle here. And if I join A and B, you guys see what we have here? We have a right angle triangle. So what is this distance here? Well, this distance here is equal to y2 minus y1, right? Because the y ordinate at this point here, what is called point C, is also y1. So this point's x2, y1. Yeah, so distance AC is equal to y2 minus y1. And then the distance BC is equal to x2 minus x1. So what we have here is a right angle triangle with lengths A, B, and C. I mean points A, B, and C. So this formula can just be rewritten as the square root of AC squared plus AB squared. Okay, so does anyone have any questions? I think you guys have already seen this before, so I'll give you guys 1 minute to take this in and reflect.
It's okay. I think we can move on.
Okay, moving on. Um, how do I move on? Just one sec. Okay. Moving on. I want to cover the midpoint of 2 points. So let me just. Yeah. So the midpoint of 2 points A and B is given by the average of the x ordinate and the average of this y ordinate. So what I mean here is we're taking the x ordinate of A and B and we're halving it, right? Because we want to find the point that's in between A and B that are equal distance from A and B. And then we do the same for the y ordinate as well. So we get this midpoint M here. So I'll give you guys a practice question. So give the coordinate of point C lying 1/3 of the length AB from point B in terms of x1, x2, y1, y2. So these are just ordinates of A and B, yeah. So I'll give you guys 2 minutes to do this question. It's really easy.
Yep. Does anyone have any ideas?
Okay, so what are we actually trying to find here? We're trying to find, so I'll just redraw the diagram here. A and B. Actually, before I move on, does anyone have any questions? Okay, no questions. Okay, so what we're trying to find here, so if we have 2 points A and B, right? We're trying to find the coordinate of C that lying 1/3 of the length AB. So should be somewhere around here. So we'll take, if we consider only the x direction, then this distance here would be x2 minus x1, right? And then this distance here would be y2 minus y1. So if we want to find this point here, that's 1/3 of the way between this point and let's just call this point C. So 1/3 the length AC. Then all we have to do is to get the y ordinate, I mean the x ordinate of A plus the distance AC over 1/3. And then we can just do the same for the y ordinate, right? We can take y1 plus the distance BC, which is y2 minus y1 over 3. And then I think all of this simplifies down to one sec. I think it's 2 over 3 x1 minus 1 over 3 x2. And then my y ordinate is the same. So 1 over 3 y1. Okay, so that's the coordinate C.
Yeah.
Oh,
So
my fault. I
um
shouldn't have used C as this point because I'm trying to find C. It should be, let's just call this point O. Okay. Does anyone have any questions so far? Any other
yeah, so
questions?
just to summarize the process
Okay,
real
moving
quick,
on.
like um
Um,
no, I was gonna say it's basically just you find a distance between A and O here. You find a third of the distance and you add it to the x coordinate of A, right, to get the x coordinate of C. And you do that for the y coordinate as well. And then you end up getting the final y x and y coordinate for point C.
okay, so another thing we can do, if we have two coordinate points, is that we can find the gradient of the line joining the two points. So I think you guys already know this. So uh, does everyone here know rise over run? Yeah, so gradient is basically defined as, oh wait, one sec. Gradient just refers to the change in y over change in x for a linear line. So this only applies for linear. Yeah, so delta basically just means change. And if you have a curve, then you would write it as dy over dt. And d is basically just delta, but then the interval's like smaller, like infinitesimally smaller. So oh, you guys don't need to know that, that's like calculus, but yeah, so just take a minute to like take this in. And
Yo, they don't need a minute.
yeah, I'm
Look,
gonna
look,
give you
look,
some
look. William,
questions
we're not
later.
trying to stall that hard,
I'll give you
okay?
guys
I can
one
just do
minute to
problems at
take
the end
just
if
have
you have
a
excess
read.
time.
And also you can find the angle by just using simple trigonometry. So you consider this triangle here, right? If I know the gradient, right? Then I know it's like the gradient is this over delta y over delta x, right? And then from SOHCAHTOA, right, I know that tan theta equals delta y over delta x. But hey, this is equal to the gradient, right? So just rewrite this as tan equals gradients. And we usually write the gradient using the symbol m. Okay, so does anyone have any questions? I'll give you 1 minute to just have a read. Okay, no questions. If there are no questions, I'll just move on. Okay, moving on to equation of a straight line. I think you guys already know this as well, but to find the equation of a straight line, we only need to know two of the following three. So we just need to know the gradient, any point on the line, or another point on the line. So like, what I mean by this is, let's say we know the following information. So we know that the gradient, let's say we know that the gradient is equal to 7, and that we know that the point 1 over 3, I mean 1, 3 is on the line. Then using this information, can you guys give me the equation of the straight line using these forms? So can someone just tell me the line that passes through 1.1, comma 3 with gradient 7? I'll give you guys 1 minute. Okay, actually I'll just walk through it. So if we know that the gradient is 7, then we know that m equals 7. And using point slope form. So point slope form is usually we usually use this form if we know the gradient and another point. So if I substitute my y ordinate, which is 3, so that's my y1, my gradient, which is 7, and then my x1, which is 1. Then I get this equation here. And then this basically simplifies to this y equals 7x minus 4. Y equals mx plus c is usually the way we represent the equation of a straight line, because this equation tells us instantly the y-intercept. Tells us the y-intercept. Because if we substitute x equals 0, right, this thing cancels, which gives us y equals c. So this is a really useful form when we're trying to sketch these linear equations. Standard form is another more uncommon form of representing the equation of a straight line. I'll give you guys some questions. Just one sec. Actually, before I cover some questions, I want to introduce you guys to the shoelace theorem. So like let's say we have some points, right? And we know that we are given their coordinates, so know that.
Wait. Can I just interrupt real quick? Um, the theorem's pretty cool, but it's not like super relevant in let's say like
And let's say we're
Olympiads.
given these coordinates, then we can actually just find the area
William, can you hear me?
that's covered. So the area of the polygon that has
I don't think
these
William can hear
points,
me.
its vertices, we can actually find the area using the shoelace theorem. So how do we actually use the shoelace theorem? Wait, Chris is asking me a question. Can you hear me? Is your volume off?
Yeah, can you hear me speaking? Can anyone hear me?
Oh wait, sure. My bad. My volume's off.
Yeah,
Yeah.
okay, cool. No, I was wondering why you were speaking over me earlier too. I thought you were being a little
Oh,
disrespectful. I was trying to
oh,
like
I
say
just
stuff,
turned
but
up my
no.
volume. Oh my God.
Nah, it's all good. No, I was gonna
My
just say a
fault.
little bit about the shoelace theorem. I think it's more relevant in like maybe computational type contests like AMC, both like maybe like Australian or American or like AIME, right? The AIME. Um, it, I'm not sure like about how like relevant it is in like more like proof type like problem solving contests, but it's a pretty cool theorem, I guess, right? I would say like don't worry too much if you don't memorize it, right? It's okay. Yeah. Anyway, I was just making a little comment on it, right? You can carry on.
Yo, that was negative aura, bro. Oh my God. Why didn't you message me earlier? All right.
Well, I thought you were just being very rude. I don't know.
Bro, you should have told me, bro. Oh my God. Okay. So let's say we have these points, right? 1, 4, 2, 5, 3, no. 1, 5. Oh, I know. Let's make it negative 1, 6, and then negative 1, 5. Wait, negative 1, 4. Okay, so if we want to use the shoelace theorem, we can just substitute these points into the formula. So the way you would lay out this is by drawing it. So if you want to find the area, you have to go in the clockwise order that these points are placed. So I just copy these points, right? So going in this direction, we get right, but then I also I repeat the first ordinate, so that would be negative 1, 4, minus, and I do the same for this. So to use the shoelace theorem, basically, I just multiply these numbers together, then also these numbers together. Yeah, so that would be equal to 1 over 2, 1 over 2, negative 4 plus 5, 12 minus 4, minus 4 plus 8, minus 5, minus 6. And that should give me a number. Um, yeah, that should give me 4. And does anyone have any questions? Okay, if there are no questions, I'll just move on. Wait, 1 sec. Okay. Moving on to Pick's theorem. Like this theorem is kind of useless, but
Yeah,
I'll just
yeah, I
go
was
through
gonna say there's no way this theorem ever
it.
comes up anyway.
Yeah. Basically, when you're trying to find the area of a figure on a plane of dots, you can use Pick's theorem if you want. So
Sorry.
basically, to use this theorem, we count the number of boundary points, which is denoted by B, I, which is the number of interior points, which is the lattice points that lie in the area, the figure. So if you look at this example here, clearly B is equal to 13. Oh wait, 1 sec, boys and girls. Um, yeah, so 13, B equals 13, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then also count the number of points inside the figure. So there's 1, 2, 3. Yeah. And then you just substitute this in the formula, which gives you a equals 8.5. So this theorem is like kind of useful, but like kind of useless. So if you want to use it, then go for it. Does
It's
anyone
it's
have
it's,
any
it's more
questions?
useless than useful, but yeah.
Yeah, that's facts, bro. That's facts. I just found it randomly on Google, but then yeah. Moving on.
Again, maybe it's useful more for like computational AMC type of questions. Yeah. Also, by the way, I just want to say I have a handout that I have a file of in which I compiled some questions about coordinate geometry or problems that can be solved with coordinate geometry, but I don't think I can post files on Zoom. So
Maybe just drop it
I'm
into Mind and Sin Discord.
is everyone here in the Discord?
Yo, guys, can you say something in the chat, please, so that we know you're listening?
Yeah, I think they're all gone. It's okay.
Um,
They left after you started explaining shoelace theorem. No, it's okay. I'll just post it onto a Google Doc and then send that to everyone as a temporary fix. I think it'll get posted in the email next week or something like that. That's fine. Anyway, you can carry on.
okay. Moving on.
Oh, wait, I added a new slide by the way.
What did you?
Yeah, I can explain it if you want.
Okay. So, guys, here's a summary. Um, yeah.
Wait, did you skip the slide?
Huh? Which one?
Oh you don't see it because I added it after you like zoomed in. I think you
Do you want me to unshare it? Will you just give me a sec?
I thought it was a pretty important slide. It's the equation of a circle.
All right. Where is it?
Slide 11.
Wait. Yo, I literally can't find it.
No, like you have like stop presenting. Yeah.
Okay, this one.
Yeah. Do you want me to explain it or like you
You can
know
do it.
what an
Yeah.
equation of a circle is?
You can present.
Okay. Wait, can I round this?
Yeah. I
Like
just click annotate.
can I? Like
Yeah.
you guys see that?
Yeah.
Okay. So if we look at a circle where the center is at the origin or 0, 0, and it has radius r, okay, I'll just choose a black color for this, or dark gray as it's called. If I have my x and y axes here, and this is my center, and I have okay, that's not a circle, but it's almost a circle. And it's got a radius r, then the general equation is given here, x squared plus y squared equals r squared. And if you think about it, it kind of makes sense, right? Because if you have any point x, y here, then yeah, it should be x squared plus y squared equals r squared, right? Because if this is distance x and this is distance y, then x squared plus y squared equals r squared. Means it's on the circle by the Pythagorean theorem, right? And it works even if it's like negative, because if you have x, y here, where, or I guess x2, y2 here, where y is negative, y2 is negative, um, y2 squared like becomes positive, right? So it'll still satisfy the Pythagorean theorem. So um that's kind of why, like, if I have something like x squared plus y squared equals r like squared, importantly, that's the equation of the circle, but that's centered at the origin. If you have a circle that's not centered at the origin, you have to like kind of do like a translation. So if I have, okay, I'll draw it down here, I guess. If I have a circle centered somewhere around here, right, maybe this is the point like 4, 2 or something, then really what I'm doing here when I have so the equation of this is x minus 4 plus, sorry, squared plus y minus 2 squared equals r squared for some radius r. And when I take some point on this circle, really, when I'm doing x minus 4 squared plus y minus 2 squared, the x minus 4 is translating it 4 units this way, and the y minus 2 is translating it 2 units this way, right? So this point gets sent by some vector, like minus 4, minus 2, down this way. It's the same vector that sends the origin of the circle to the origin of the coordinate plane, right? So actually every point on the circle gets sent by the same vector. And in fact, if you send like every point, you just get the circle centered at the origin with radius r. So what this minus 4 and this minus 2 are doing is it's basically shifting our circle centered at the origin to the circle centered at like hk, right? In this case, 4, 2. So yeah, that's the general equation of a circle. Very cool. Great, we can move on to some like computational problems. And after this, I'll go over some maybe more like Olympiad style problem solving problems. Yeah, William, you there?
Oh, that was negative. Or oh, okay, moving on, guys. Okay, I wanna go over this random question I found. Okay, I'll give you guys 10 minutes to do this question, or maybe 5 minutes. I'll give you guys some time.
Oh wait, let me clear them. Cool. So Isabel got an answer. Is it the correct answer? Probably is. I don't know. I haven't actually tried the problem yet. Um, but good job. Wait, how do you use problem? It's wait, y coordinates are 0, 1, 4, 5. Actually, wait. If I might just talk a little bit about this hint here. So notice in the hint, what we do is we place the point that's on y coordinate 0 at 0, comma 0. So that's like often a nice way of like setting up your coordinates because you kind of have the freedom to choose where your axes are, right? Where your points lie relative to the axis. And it's always like it's almost always a good choice just to put one of the points at the origin at 0, 0. It just makes like a lot of things simpler. And then once you put, you know, your like point at the origin, maybe you can do something like making another point like x comma 1, for example, right? Like the point at y coordinate 0 is 0, 0. Then the point at y coordinate 1 could be like, you know, x1 for some constant x. And then you can use that to work out where the other points should be, like in terms of x. And then maybe you can, you know, use that to like pin down the value of x and therefore get the area of the square.
Yo, do you guys need more time or do you want me to present the solution now? Like, also make sure to like share your working as well. Like, Isabel, how did you get 17? I'll give you guys 2 more minutes.
Okay, I'll post the questions in the handout that's on the Google Doc into the chat real quick.
Okay, guys, I'm gonna start presenting the solution now. So, guys, if we look at this square, right, we know that this distance here is equal to 1, right? Because this point has y ordinate of 1. Then we know that this distance is 5. We can actually draw bigger square that has the square inside of it. And then since this square is touching all edges of this larger square, these 4 triangles must be congruent, right? So if we find the area of this larger square minus the area of the 4 triangles, then we get the smaller square, right? Well, the bigger square is equal to 25, right? Because it has side length of 5. And 5 squared equals 25, right? Yeah. And then the area of the triangle, we know that this distance here must be equal to 4, right? 5 minus 1. And then since these triangles are congruent, just copy this 4 down here. So redrawing the triangle, you have 4 and 1. And the area of one triangle is equal to 1/2 multiplied by base times height, which gives me 2. And then since there are 4 triangles, you multiply each area by 4. You multiply the area of each triangle by 4, yeah. That gives me 8. So 25 minus the area of 4 triangles gives me 17, which is answer B. So does anyone have any questions? I'll give you guys 1 minute just to have a deep think.
Okay, I don't think this wants a deep think. Another way you can do it, by the way, is just literally like trying to find out all the coordinates of the points. So, like I was saying earlier, or the way that I was thinking about it is that if this point is 0, 0, and you say this point is like x1, then actually, yeah, if you notice that since you know this height here is 4, and these triangles are congruent, you must have that x here is actually equal to 4. So if this point here is 4, 1, then using the distance formula that we had earlier, this side length must be square root of 4 squared plus 1 squared is root 17. So the entire area of the square is just 17 like units squared, right? But yeah, so that's another way of doing it. Literally just like directly computing the side length to the square and then find the area. I think we can move on, to be honest. This is we have more questions. It's okay. Because I'm gonna present like some like Olympiad questions at the end later as well.
Okay. Alright, moving on, boys
And girls.
and girls.
You gotta stop
Oh,
saying that.
I keep thinking it's mathematics, bro.
I think you're stupid.
Okay. Guys, just have a go at this question. I'll give you guys 20 minutes. Yeah. For like 2 minutes. No, 5 minutes. Yeah.
By the way, when it says from the interval 0 to 2017, it means a random number between 0 and 2017, including 0 and 2017.
Okay, you guys want more time or do you want me to present the solution? Also, you guys, if you have the answer, just drop them in the chat. This is a judgment-free zone. Like, even if you get it wrong, no one's gonna judge you, so trust. And I'll give you guys 2 more minutes. Okay, Maki, and Isabel, both have the right answer.
Yeah,
Can
very
you guys
nice. More time? Uh, no, I might present the solution now. Okay. Well, I'll talk about a little bit about this hint that William gave pretty early, to be honest. I'm not sure why he was giving a hint after 5 seconds, but um, I mean, I guess it's like maybe already hint that this question's in the geometry tutorial, given that it doesn't necessarily resemble geometry at first. But if we look at this hint, something you can do, and this is a pretty common idea, maybe, so maybe keep this in mind, is when you're looking at these probabilities of like two people choosing numbers, you can represent it in a type of graph. So on the x-axis, you have the number that well, Chloe chooses, and on the y-axis, you have the number that Lauren chooses. So if we take a random point in this graph, which is between like 0 positive 2017 and 0 positive 4034, if we take some point let's say here where this is like some point like 1800 on the x-axis and 2000 on the y-axis, this point here represents like the event that Chloe chooses 1800 and Lauren chooses 2000, right? And in this case, this does fall under the event that Lawrence number is greater than Chloe's number. So if you have a look at, okay, by the way, I'm gonna, okay, the scale's a bit off because here clearly here 2017 looks about as big as 4034, but okay, oh well. Actually, I don't like that. I'm changing that. Well, I can't delete Gong's work. Yeah, sorry. Okay, that's like a bit extreme now, isn't it? Like about here. Wait, look, okay, can I just, okay, yeah, cool, thank you, right. So 2017 is obviously exactly half of 4034, right? I guess I need to delete whatever, I was writing over here now. But anyway, any individual point on this represents some real number that Chloe chooses and some real number that Lauren chooses. So we kind of want to like have a way of, being able to determine when is this condition that Lauren's number is greater than Chloe's number, when is this condition fulfilled? Okay, so I mean, I think something maybe like kind of, like not too hard to see is you want to draw the line um with equation y is equal to x. Well, the reason you want to draw this line is that the condition that Lorentz number is greater than Chloe's number is the condition that y is greater than x, right? That's this region up here above the line y is equal to x, right? Because of your like if the y value is higher than y is equal to x, clearly y is bigger than x, right? Um, I'll try to do a bit of better shading here, but yeah. So we're interested in this region. Basically, if any point lies within this shaded region, it satisfies the conditions. And if it, well, okay, it should just be this region here, right? Like I don't really care about this because this is kind of outside of probability space. Anyway, because if our probability space really is just this rectangle, bounded by 2017 and 4034, right? Like any point in this rectangle is uniformly as likely to appear as any other point. And any point in this shaded like thing is satisfies the conditions, right? So basically, we want to find what percentage of the shaded area is the total area. And if you just, because we know this is half, right? So this is 2017, this is 2017, and this is 2017, right? These two are equal because this line y equals x and this is half. So I guess one way of looking at it is you can kind of split it up like this. This is a quarter of the area, like this black part's a quarter of the area, this black part's a quarter of the area, this black part's a quarter of the area, and then this white part's a quarter of the area. So the total black part of the area is just 3/4. So that's option C, and then we're done. Cool. So that's a way of I guess geometrically looking at probability spaces. Great. Moving on, perhaps.
Okay, moving on to the next questions. Next question. Okay, this is the last question before I dip, guys. So just have a go. I'll give you guys 10 minutes
Wait, the last question before what?
before I dip.
Oh, why?
Right, because or just message me. One sec. Has anyone figured out the answer to this question? Like, if you have the answer, just drop it in the chat, and I'll give you guys more time, like maybe like 5 minutes. Also, by the way, who here is doing incident mode too? Like, if you're doing incident mode too, just say it in chat. Oh, Isabel's doing it. Nice. Yeah, it's good to see. Oh, Josie's doing it too. Alright, good luck, guys. I hope you guys pass incident mode too, and hopefully win a medal. Okay, 4 more minutes. Okay, do you guys want more time or do you want me to start presenting now? I'll give you guys 2 more minutes. Okay, Marky has an answer. Marky says it's E, 7/16. So we'll see if this is true. But good job on
Actually,
finding
wait, let me
out.
try the problem as well. Hmm.
Okay. I'll give you guys 2 more. Do you guys want more time or do you want me to start presenting now? Okay, I'll go over the solution and then if Chris has a different way of doing it, Chris can present the other solution.
Yeah, I usually should listen.
Yeah.
Okay.
Okay, so what we can do
How,
here,
how inspiring.
well, if I draw, if I set point C as 0, 0, then we can actually obtain the points E and A, right? Because we know that CE is equal to 16, so E must be equal to 16, 0, right? Do the same for A. AC is equal to 12, so A is equal to 0, 12, right? That's facts. Now we can do the same for B. B is 9, 0. D is 4, 0. Now, how do we get F? Well, this is where we can use similar triangles again. So if I draw this line here, I get this triangle here, right? F, E, and also A, E, right? Someone sent a message. Isabel also says it's 7/16. Okay, good job, guys. Um, so we know that FE is equal to 5, right? AE is equal to 20, and AC is equal to 12. All right. So we can actually find the height of F, so the y coordinate of F, by just using similar triangles. So I know that, let's call this point here P. We know that FP over FE must equal AC over AE, right? So FP is therefore equal to 3. So basically, we can use the y ordinate, we can set the y ordinate of F as 3. So it'll be something 3. Now we can do the same for the x coordinate. Since this is a similar triangle, right? You can find PE, so PE will be equal to um Okay, I can use Pythagoras here. So 400 minus 144 equals to. Well, just give me a second. I think it's 256, I think. Yeah, it is. Okay, so therefore CE must be equal to 16. Is it 16 or yeah, 16, yeah.
It's 16. It's a 3-4-5 triangle scaled up. So okay.
Yeah, okay. And then that means PE must be equal to 4. So I know that PE is equal to 4. So the x coordinate of point F must be equal to 16 minus 4. That'll give me
Wait,
12.
bro, are you wait, why did you use Pythagoras? Isn't it just 4 plus 12 at the bottom?
Where, but then don't you have to find PE to find the coordinate of F?
No, wait, what were we doing for 16? Like 400 minus 144.
It's for this triangle here.
Wait, why did you need 400 minus 144?
Because to get, oh, wait, that's facts, bro. That's facts.
Yeah.
But yeah. Okay, it doesn't matter. Gives you the same answer. But anyway, we have the point F now, right? And basically we can find the area of the larger triangle, which is um ACE, and the area of that is equal to 1/2 multiplied by 16, which is equal to CE, multiply by 12. So that gives me 96. Is that facts? Yeah, it is. Okay.
Hmm.
We can also find the area of BDF. So let's do it on the side. Point B is 90. Point D is 40. And then F is 12.3.
Point B is 0, 9, isn't it?
Wait, what?
Point B is totally 0, 9.
Oh, that's facts. Okay. And then from these 3 points, we can just use the shoelace theorem. So just erase everything. So we have 0, 9, 4, 0. Then I think it was 12.3, I think. So shoelace theorem. So we have to go clockwise, remember. So actually, I'll just start from 4, 0. So 4, 0, and then 12, 3, 0, 9, and then I copy the first coordinate again, minus, same thing. And so for Shoelace theorem, we connect these ones, and then also these ones. So that should give me 4 over 12. I mean, 4 multiplied by 3 plus 9 times 4, so that'll be 48. Plus 0 minus 36. So that'll give me 24 equals 12. Wait, no,
Um,
14. Wait.
why'd you do, wait, what, how'd you get 48, by the way? Isn't it 12 plus like 108?
Wait. Yeah, that's facts. And then 1/2 multiplied by 120. Okay, I think that's 84.
Yeah, good.
So that give me 42. And so it'll be 42 over,
96, right?
yeah. So they'll simplify to 7 over 16.
Yeah, divide top and bottom by 6.
So Chris, do you have a different way of doing
Yeah,
it?
yeah. I mean, I can do it without the shoelace formula, right?
Yeah.
Yeah, I mean, I'll just quickly present like the alternative solution. I mean, shoelace formula certainly makes us um simple, as straightforward as in, right? Just calculate the coordinates and then just apply the theorem. But again, you might not know the theorem, and I wouldn't blame you if you don't, because it's not like um yeah. Okay, anyway, if you could clear the board, I'll present my solution. Okay, so the key is recognizing this triangle, right, as a 3, 4, 5 scaled up triangle. Like if you look at the side lengths, it's 12, 16, and 20. Well, this isn't the key, but it makes it a lot like quicker, right? This is a 3, 4, 5 triangle scaled up times 4, right? Okay, cool. Now we're gonna use similar triangles a little bit. Okay, let's drop this perpendicular here like we did before. And we have that this length here is 3, this length here is 4, because it's the same triangle, right? But here's the hypotenuse is 5. So we've scaled it down by 4. So now this is a 3, 4, 5 triangle. This is no longer 12, this is now 8. So we split the base into 4, 8, and 4. Okay, let's drop another line here. This length is 5 and this is 4 because we have another 3, 4, 5 from the triangle. This is no longer 5, this is 10. And finally, let's okay, I mean the general gist, sorry, I should have explained this earlier, is we're gonna find the area of the big triangle and minus the area of these surrounding smaller triangles to get the area of the triangle in the middle. Okay, so the area of this bottom left triangle is pretty easy to calculate, right? This one is just 18, half times 9 times 4. To get the area of this bottom right triangle, we split into two triangles, right? This one's pretty easy to get. It's 12, half times 3 times 8, and this one is 6, half times 3 times 4, right? So now we have one last triangle to work out. It's this one at the top. That's kind of like a really long and obtuse one. What we're gonna do is we're gonna minus. Oh, sorry, I don't think I needed this triangle up here. Did I? Do I? Clearly not, right? Okay, that's fine. We're gonna take this larger triangle, this one, which I'll color in like blue, right? We'll take this larger triangle and we'll subtract this orange triangle, right? And clearly, if we take the blue one and we subtract the orange one, we'll get the skinny, long, obtuse one. So the area of the larger blue triangle is well, it's the base here is 4 plus 8 is 12. And the height here is 3 plus oh sorry, well this is if we carry over the this length from here, this length here is 3 and then this length here is 6, right? So this triangle has 6 for its height and 12 for its base. So it's 30. Oh, sorry, the skinny triangle is 36. The big triangle is 9 and 12. So that's 54 for its area. And then we want to subtract what did I color? I colored it orange earlier, right? That orange triangle, which was the smaller one. And that triangle, if you just read off the graph, has 12 and 6. So that's area 36. So it's 54 minus 36 is just like 18 or something, right? Cool. So this triangle has area 18 as well. In fact, they all have, so the three triangles all have area 18, which is kind of interesting. So the area of this funky triangle in the middle is the large area, which is 96, minus 3 times 18, which is 54, which is equal to 42. And you do the same thing. You do 42 for the triangle in the middle, divided by the total area of the large triangle, 96, is 7 over 16. Okay, cool. Circle E, go to the next question. Done. Great. Um, okay, I'll share my screen now since William is maybe like, leaving or something. Oh, I'm sharing. Also, can I just say this? I'm sharing a link to it, am I not? Wait, can you see my screen? Yeah. Also, can you not type in the link? Because I'm pretty sure everyone has edit perms. I'm sure no one would do anything bad, right? Okay, the next question here is a scholarship calculus question, which I'm not going to do because I don't want to do that. Okay, what I'm going to do is instead, I'm going to go through one or two of these problems I've compiled on this sheet. Wait, do you guys see the problems that I'm sharing right now on the Google Doc? Cool. So actually, first I'll talk a little bit about like coordinate geometry, right? And using them to solve Olympiad problems. So generally, what this looks like is, first of all, you want to define your problem in a nice way, right? Maybe I put point A on the origin, and then I'll try to find the coordinates of every other point, right? Maybe I'll define point B to be some point like x, y, right? Or x naught, y naught, or like PQ or something. And I try to calculate the equation of every line. Maybe I try to calculate the length of every line segment, or try to get the like coordinates of every other point using these variables. So eventually, I might have the gradient of every line. And maybe the question asks me to prove that two lines are perpendicular. Well, maybe if you guys recall from school, or maybe if you don't, I'll just bring it up as a fact. The gradients of two perpendicular lines always multiply to -1. That's kind of like the condition for two lines being perpendicular. The gradients multiply to -1. So let's say I calculate that the gradient of the first line is 1 over p, and I calculate the gradient of the second line is -p. Well, then I solve the problem, right? Because 1 over p times -p is -1. Therefore, the two lines must be perpendicular. So that's kind of when you would use coordinate geometry, right? The issue with coordinate geometry sometimes is that you can't describe the equations nicely. Like, what if I have 3 circles in my problem? Yeah, I know the general equation of a circle, but it's really, really annoying trying to like make equations using them because they're quadratics, right? Like, I don't want to have to write out like all these equations and solve a bunch of quadratics, and then the quadratics probably turn into quadics, and I can't solve those, right? Sometimes you can't just bash out a question. And that's okay, right? You can't solve every question using coordinate geometry. I'm not saying you can. In particular, when a question has something like a lot of angle bisectors or circles or weird conditions, like um, some weird line segments being equal, and you can't like rigorously define everything in terms of points and lines, then maybe coordinate geometry isn't the best like option, right? Because you can't easily just define every equation, every point. That's ultimately what you want to do with coordinate geometry, right? You want to be able to define every point and every line and every segment and every whatever. So first of all, if you see a question, like some of these questions, right, where there's only squares, for example, we'll take NZ Squared Selection Test 2024. This was in the January camp this year. Let P be a point inside square ABCD. Prove that the perpendiculars are concurrent. You see a square, you see perpendiculars, you see lines. That's everything that's easily able to be defined using equations of lines and coordinates, right? Great. Just start, listing out variables and bashing it out. Again, like if you see something where it's like lengths or like perpendiculars or just lines and like parallel lines where there's no circles, then like see if you can coordinate bash. I mean, a lot of times you can. Sometimes if you look at the last question here, right? Let ABCDE be a convex pentagon such that blah 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 is the midpoint is the circumcenter. These ones are a bit harder. Sometimes you have to convert weirder conditions like circles and angle conditions into nicer ones like perpendicular conditions, right? Like you want to do a bit of synthetic geometry before you start bashing using coordinates. For easier problems, you can oftentimes just set up a coordinate like system right away. Yeah. So maybe I'll go over the first problem here as an example of how to actually properly solve or like a proof type question using coordinates. The other thing with coordinate geometry is be careful when you're using it, right? Be very, very careful. Because if you make any small mistake in your algebra, your entire like reasoning kind of goes wrong, right? And you don't get anywhere, you don't make any progress. It's really hard to make any type of partial progress when you're doing coordinate geometry, right? Like if you spend an hour writing down equations, calculating equations of lines, of points, of segments, and you mess up one algebraic step somewhere in the middle, you get a 0 out of 7. Yeah, you don't get any partial marks for messing up a bash. So it's sometimes it's quite a risk, especially if you don't know how long the algebra is going to take you. Sometimes it can get really messy, and maybe you're not able to actually complete it, and you waste a lot of time. Um, so I would recommend only going for a bash if you know that you can easily define all the lines and equations, and you can like work. You have enough time to work through it, right? It is a time investment if you're trying to do it in contest. Um, okay, I'll go with the first problem. I might just set up a gem. Or where? Uh, where? How do I see my own screen? Um, okay, I don't know. I might just go make a Jamboard because I don't know how I'm meant to be seeing my own screen. My screen. Hmm. Ah, cool. Never mind, found it. Okay, I'll just write on the Zoom meeting then, like what we were doing before. Okay, so the question is, okay, what's the question? Sorry. Let ABC be a triangle with AB equals AC. So we have an isosceles triangle, and we're letting H be the orthocenter. I hope you guys are familiar with what an orthocenter is. Please tell me if you're not. Point E is the midpoint of AC, and point D lies on side BC, such that D is BC 3 times CD is equal to BC. So DC is like a third of the way to B from C. Um, Prove that BE is perpendicular to HD. Okay, cool. So I'll quickly draw up the problem here. So we start with a isosceles triangle. Oh, sorry, so someone else already drawn it? Wait, why is it? Is everyone else seeing 2 copies of this? Am I going insane? Oh, oh, sorry. Oh, okay, no, I see what's going on. My bad. Okay, I'll start with a isosceles triangle like this, and I'll call it, A, B, C. And I'll let my orthocenter be H here. So the orthocenter is the well, it's where the 3 angle bisectors, not angle bisectors, sorry, it's where the 3 altitudes intersect, right? So these lines here are perpendicular. Okay. Um, you have point D, oh sorry, point E is the midpoint of AC. So we have point E here such that these 2 lengths are equal. And you have D such that uh it's a third of the way between D and C, right? The condition was, I believe, 3 times CD is equal to BC. And it asks us to prove that BE and HD is perpendicular. So we want to show that this is a right angle. Okay, so how do we start? Um, well, when we start with a coordinate system, you want to choose like where you're going to put the origin, right? I'll give these some names too. As well. I guess I'll call this one like F, and then this one maybe I'll call this like, okay, I'll call this like P, and I'll call this point Q. Okay. So where do you guys suggest putting the origin? Any ideas? Yeah, there's no like wrong answer here, by the way. Just to clarify. Like I think yeah, P is a pretty good idea, right? And the reason P is a pretty good idea is um because it's kind of in the center of everything, right? Like for example, if P is the origin and the C, like I give the point, x0, then B would be negative x0, right? So it's kind of symmetric in that thing. And it's also nice that, AP is the y-axis, right? So H um lies on the y-axis and BC is the x-axis. And that seems pretty nice, right? It doesn't have to be like that. I'm sure you can make H the origin if you want to. You can make B the origin, you can make A the origin, you can make anyway the origin. I'm sure it wouldn't be like terrible. But maybe P is the nicest one, right? So let's just mark that down. We'll have P as 0, 0. And maybe we'll introduce some like letters for like A, B, and C now, right? So maybe we'll have A, B. Well, we know the x coordinate of A is 0 because it lies on the y-axis. And maybe we'll just call the y coordinate A, right? So let A be, let this be. Oh, actually, we could go one step further and no, because what I'm going to do is the thing. Okay, oftentimes, right, when you're defining coordinate systems, you can control the lengths as well, right? So if I have some square A, B, C, D, right? I mean, I know there's no square in this problem, but imagine some problem had some square A, B, C, D. Like you could make the side length of the square X, but you could like just as like well make the side length 1, right? Because you can just scale down the entire problem such that the side length of the square is 1. And that maybe just makes the problem nicer to work with, right? So that's kind of what I'm gonna do. I'm just gonna say that the length from P to C is length 1. So that means that C is the point 1, 0, and B is the point negative 1, 0. And I hope everyone like, can see why I'm able to do this, right? Like if C isn't the point 1, 0, I can kind of just scale the entire problem, like apply some scale factor such that C lands on the point 1, 0, and everything still stays the same, right? Okay, so what is point D now? Like using we've defined our P, A, C, and B to be these points. What is D? Yeah, great. Because DC is a third of the way to BC. That means that DC is length 2/3. Therefore, PD is length 1/3. And so that means that the x coordinate is 1/3. And we know that it lies on the x-axis. Therefore, its y coordinate is 0. So D is the point 1/3, 0. Okay, great. Oh, sorry, this point here should be H. Okay, what is the point Q? And this is generally what you want to do with these problems, right? You kind of just find the coordinates of literally every point you can and every line you can. Like the end goal here is we're going to try find the gradient of BE and the gradient of HD and show they multiply to -1. Oh, sorry, wait, did I say Q? I meant E, but I guess on we can ask for Q as well, right? Can we? Um, okay, never mind. Wait, so sorry, not Q yet. I meant to ask for E. We'll do Q later. Remembering here that E is the midpoint of line segment AC, which I think we learned the formula for earlier. But even if you don't remember the formula, it's not too hard to like figure it out, I think. Does anyone have any ideas? Okay, if no one knows, I guess I could just say it. So recall that for a midpoint, between like X and Y, if X here has coordinates PQ and Y has coordinates RS, then M is simply the average of the two x coordinates and the average of the two y coordinates. And that's literally just because, I mean, you're just in the middle, right? So this like the x coordinate of M is just the average of x and y, and the y coordinate is the average of x and y as well. So if we look at point E here, like you know, with that information, what should the x coordinate be? Yeah. So the x coordinate should just be a half, right? Because here we have 0, here we have 1. So it's right in the middle, it's a half, right? And if you look at the y coordinate, at the bottom here is 0, at the top here is a. So the y coordinate is exactly halfway between, which is a over 2. So E is the like E has the coordinates 1/2 a over 2. And also, might I like add, I have not done this problem using like Cartesian coordinates before presenting it. Like this is kind of the thing with Cartesian coordinates, right? It's like I know that this will work if I do everything properly. I don't need to like check to make sure that I know how to do it. Like you definitely can do it. Like it will work out because the problem is true, right? As long as you're diligent and just go through everything methodically, you will get the correct answer at the end. Um, okay, so E is this. The next well, the final 2 points we have to like find, I guess, are Q and H, right? So we probably want, I mean, H is kind of defined by um Q, right? Like H is defined as the intersection of AP and BQ. So we probably want to find point Q first. Okay, but that's not so easy. How do we find what point Q is? Well, we have to note that point Q, like what is point Q? Point Q is defined as the point on AC such that BQ is perpendicular to AC. Okay, so how do we like find that, right? We want to use the fact here that uh, lines that are perpendicular have gradients that multiply to -1. So what does like no like knowing that we actually know the gradient of BQ because we know the gradient of AC, right? So I'll just mark that down as M subscript BQ, right? I mean, I guess first of all, wait, what is the gradient of AC? Where M here represents gradient and the subscript of AC just represents the gradient of the line AC. You know, remembering that, yeah, gradient is just rise over run, right? So our rise here is -a because we're or well, okay, like the difference in y is like a, and the difference in x is 1, but it's like negative, right? So it's -a. Good job, Isabel, right? That's correct. Um, so minus a. So what is the gradient of BQ then? Yeah, remembering that perpendicular gradients multiplied to -1 is -1 over the gradient of AC, so that's just 1 over A. Okay, so now we have the gradient of the line and we have a point on the line. And when you have a gradient and you have a point, you actually just have the equation of the line. And here you use the point gradient. I don't know what the equation is called. Basically, it says that uh if gradient, okay, that's bad writing, but like if you know the gradient, right, is equal to M, and you know a point, right? I think it's normally just denoted as x0, y0. So here x0 and y0 is just a point on the line. Then the equation is y minus y0 equals the gradient times x minus x0. And you can maybe like kind of think about why this works. The general gist of why this works is if I have some line here, right, and I have some point x0, y0, and the gradient is m, then if I take any point x, y on it, no, what we're saying is y minus y0 is equal to this gradient times x minus x0. So if we have some point x, y, the difference in y is represented by y minus y0, right? And the difference in x is represented by x minus x0. So you have, again, that like y minus y0 divided by x minus x0 is exactly the gradient, right? That's why this equation works. You're basically just saying that like the gradient is m. Okay, cool. So using this equation, we get that okay, I'll just denote equation of BQ is equal to, well, the equation of BQ is we're gonna use the point B's. Okay, I'm just gonna quickly go through the rest of the proof because we're maybe running out of time a bit, right? So the equation of the line BQ is y minus the y coordinate of B, which is just 0, is equal to the gradient times x minus the x coordinate of B, which is just x minus -1, which is x plus 1, right? So the equation is literally just y equals 1 over a times x plus 1. Cool. And now when we're trying to find point Q, we can define it as the intersection of the lines BQ and AC, right? And when you're trying to find the intersection of two lines, what you do is you just solve for like the x and y values of the two lines, right? So the equation of AC is very similarly, if you're using the same line equation here, using the gradient of -a, you have if we just use the point like y c here, y minus 0 equals -a x minus 1. Because the equation would give us y minus 0 equals m times x minus 1, using the point 1, 0 as c. And the gradient is -1 as shown up here, right? Okay, so we've worked out the equations of BQ and AC. So we just solve these two simultaneous equations to get the intersection of the two lines, and the intersection is obviously Q here, right? So solving for this, you have 1 over a times x plus 1. I'm just gonna do this on paper here. 1 over a times x plus 1 equals -a x minus 1. X over a plus 1 over a equals -a x plus a. X 1 over a plus a equals a minus 1 over a. X equals a minus 1 over a plus 1 over a, which is equal to, if we simplify this, a squared minus a over a squared plus a. Okay, so we get x is equal to someone should probably check my work just in case I'm wrong, because like I said, it's easy to like get stuff wrong when you're doing stuff like this, right? I think the answer is a squared minus 1 over a squared plus 1 if you solve for this. Is that true? Someone can confirm. I'm just gonna assume it's true unless someone tells me otherwise. Wait, sorry, I'll just quickly check again. Negative x plus a plus a. Yeah, that should be good. Oh, sorry, for point Q. What I did is for point Q, we have the, because we know point Q lies on the line BQ, and it also lies on the line AC. So it must satisfy both of these like equations, right? Y equals 1 over ax plus 1 and y equals negative ax minus 1. So if you solve for these equations at the same time, you should get the value of x and y for the point Q. So we have, if we solve for it, we get x equals a squared minus 1 over a squared plus 1. And if you sub that back in, you get y equals, oh, sorry, that's a pretty bad C. Let me redraw that. Wait. Plus 1, 2 squared plus 1. I think you get just like 2a over a squared plus 1. Yeah. Oh, sorry, wait, Isabel, wait, how'd you find the gradient of dh? Yeah, like specifically, how do you find what h is? I thought you needed to find q to find what h is. Oh wait, no, wait, sorry, yeah, Isabel's totally right too. I got a bit lost in what we were trying to do. I thought we needed to find point Q to find the equation of BQ. No, we were trying to find the equation of BQ. I thought we needed to find point Q to find that. Yeah, ignore me. Um, no, Isabel's totally right. Yeah. This is what happens when you kind of like stop thinking a bit. Okay, so what I was doing, like, okay, I know I said you try to find the equation of every the coordinate of every point, and you can, and I was doing that. I was literally about to find the equation of the coordinate of every point, and that's fine and well, but it is a bit of a waste of time, right? Because you don't need to do that. Yeah, specifically, we're only trying to find point H here. Like you could find the coordinate of Q, but you don't really need to. So maybe I did waste a bit of time here. Yeah, sorry about that. Well, great. I guess the next step would have been to find H, which is yeah. So okay, I just did a bit of extra work, which is okay. Honestly, that wasn't bad though. I feel like that does illustrate a point on how to find points. Like if you did for some reason need to find point Q, you get the two equations of the two lines it lies on, and then solve the equation simultaneously, and you get some equation that looks like x equals x a squared minus 1 over a squared plus 1 and y equals 2a over a squared plus 1. And notice that like this is like a pretty common type of expression you'd be getting, right? We have like squares maybe in like the numerator and denominator of some fraction, and it looks kind of messy, um but yeah, it does often look like that. Okay, sorry. I'll quickly finish up. So okay, so you have the equation BQ here, and you want the intersection with the y-axis to find point H. The intersection with the y-axis is just when x equals 0. So when x equals 0, you have y equals 1 over a. Therefore, H is just the point 0, 1 over a. So we have points B, E, H, and D now, which means we can find the gradients, right? So the gradient of line BE is rise over run, which is difference in y values, so that's a over 2 minus 0 over the difference in x values, which is 1 over 2 minus negative 1, which is just a over 2 minus, a over 2 divided by 3 over 2, which is 3a over 4. And in the equation of dh is again just rise over run, change in y over change in x. Change in y is it's 1 over a. Here's 1 over a, here's 0. So it's 1 over a minus 0. And in the change in x is here is 0, and in this one is, what is it, like, okay, I must have done my algebra wrong somewhere. Wait, a over 2 minus 0 over 3 over 2. Yeah, sorry, this is not 3 over 4. I don't know what I was doing here. It's it's just a over 3, right? Because it's a over 2 over 3 over 2, so it's a over 3. Yeah. 1 over a minus 0, and then we have change in x is from 0 to a third is minus 1 over 3 equals negative 3a. Yeah, great. So you have that the two equations are, the two gradients multiplied to -1. So like QED little proof thing. So that's what we wanted. Great, we finished. Actually, I think my diagram must be like really wonky because apparently the gradient of DH is supposedly 3 times the gradient of AC, but on my diagram they look almost parallel. Um, yeah, okay, well, yeah. So notice how that problem took me like 30 minutes to present, just because like when you're doing these types of problems, sometimes it is okay. This problem really shouldn't have taken that long to be honest. Like honestly, if you're doing it and you're comfortable with like doing equations and stuff, it probably only takes like 10 minutes. So that's fine. So yeah, you guys can try practice on a few of the problems like earlier, not earlier, like on the first page here. I think the first 4 are like not that bad. The fifth one maybe a little bit harder. Um, but it should still be doable. I think all of these problems are very doable. So yeah, cool. You guys need to go now. You can go. So yeah. No, if you guys want to stay, we can do another problem. Um, do you guys like have any questions or anything? No, but so I guess I'm like leaving us and stay. Okay, bye bye, Maki. Oh, sure you left. Um, as well as I was gonna say, is everyone else here staying? Because like I could just carry on the lesson. That'd be kind of funny. Okay, bye. Okay, cool. Everyone's basically gone here. I'll just end the recording to be honest. Try. Oh, maybe I won't. Do you think I don't want Nicole can get mad if I carry on the recording for like another 30 minutes and they have to upload like a 2 hour, like a 2.5 hour video to YouTube. I'm sure it'll be fine. They no, they can edit it if they need to. I can edit it if I need to. Um, okay, do you want to go through like problem 2 or do you have like any other suggestions? Like any you can suggest any problems. No? Like just problem 2 then? Is that fine? Okay. Funny story about this one. So this was used in the January camp this year, and I did not solve it. Oh, why is there a 4 there? Okay, that's a typo. That shouldn't be there. Anyway, it was problem 4 on the Friday test. Funny story. I didn't solve it. It was a bit too hard for me. Honestly, the like non-code bash solution wasn't even that hard, but yeah, I could not find it. And then after the test, everyone was just saying it's code bash. And then after that day, I learned if there's a square and no circles and no angles and it's just a square and lines and perpendiculars, just use Cartesian coordinates, right? Okay, so I still haven't solved this problem yet, by the way. I just know it's possible with Cartesian coordinates. So you know what? I guess we're trying it together. Um, great. Let's begin. Let P be a point inside square ABCD. Prove that the perpendiculars from ABCD to BP. Oh God, I've concurrent. Okay. So let's start off. Oh shoot, a diagram probably can't take too much space. Probably shouldn't take up too much space at least, just because you often do quite a bit of writing when you're doing these coordinate dashes. Okay, nice square A, B, C, D, and I'll just pick a random point P inside. That looks good. That is not a good line. Okay. Right. God. Man. Okay, so we're drawing a perpendicular from A to BP, from B to CP, from C to wait, was it? Was this right? A to BP, yeah, B to CP, C to DP, and D to AP. Okay, cool. C to DP. And D to AP. Huh. Okay, maybe I need an actual good diagram for this because these points don't look collinear at all, concurrent at all. I mean, okay. Actually, the first thing I'll note is that notice how there's like 4 lines that we have to prove are concurrent, right? Where concurrent means they meet at one point. I'm just gonna do it for 3 of these lines because like if you do it for 3 of these lines, you've basically done it for 4 as well, right? Kind of by like rotational symmetry because you can kind of just rotate the entire square. Like instead of it being A B C D, I can like rotate it so that it's like B in the top left and then B C D A, and then if I prove it for like 3 lines in that orientation, then like I can prove like any of the 3 lines basically, right? Therefore, all the 4 lines must meet at the same point. Um, if you kind of get what I mean. So I'm just gonna do it for 3 lines. Uh, so I'll do it for the perpendicular from A to BP, the perpendicular from B to CP, and the perpendicular from C to DP. And then I'll leave out the perpendicular from D to AP. So I'll just get rid of that one. Um, so yeah, apparently these 3 lines, maybe I'll color them a different color. Apparently they should, and they really, they really don't look like they do though, which is like a bit of a problem, but it's whatever, I guess. Um, so let's start by just setting up our variables again, right? Okay, how do we want to how do we want to do it this time? I mean, setting up like our axes, right? Our coordinate system. Like where should we place 0, 0? Hmm. I'm actually not sure. I don't normally do these bashes. I mean, there's like 2, I guess, obvious ones. I mean, one way of doing it is just setting d to be 0, 0. Or I guess you could set the center of the square to be 0, 0. I'm not exactly sure. Which one would be nicer or like easier? Um, who knows? Who cares? I'm just gonna wait. Do, I think there's probably more symmetry if I set the origin to be the center of the square, right? I think I'll do that just because this problem is already like quite symmetric in every regard. So I'll set the origin to be 0, 0, 0 to be right in the center of the square. Okay, that means that the rest of these I'll have A as -1, 1, B as 1, 1, C as 1, -1, and then D as -1, -1. Yeah, cool. Um, and I'll take our point X, right? To literally, oh, sorry, our point P, I mean, to just be some random point, like I'll just call it PQ, where P and Q are both between -1 and 1, right? So they lie within the square. Um, okay, let's try work out the like equate like I mean, well, to show that three lines are concurrent, what you want to do is you need to find the equations and show that there's like some value of x and y that satisfies all three of the equations at the same time, right? I.e., it lies on all three of them at the same time. So yeah, let's just start bashing it out, right? Let's just start getting the equations of everything. Okay. Um, I mean, we already have all the points, like the coordinates defined. We just need to start working out like gradients and lines. So let's look at the gradient of PQ first. Not PQ, BP. That's like 1 minus Q over 1 minus P, I guess. 1 minus Q over 1 minus P. Uh, so therefore, the gradient of AP, which is perpendicular, not AP, um, I'll call this point like X. I'll call this point Y, and I'll call this point Z. These are like the intersections of the lines, right? So you have the gradient of the line AX is -1 over the gradient of BP, which is just, I mean, you flip over the fraction and you like multiply by -1, right? So, okay, I hope you guys are following. If you guys are here, honestly, maybe you guys aren't here, but that's okay, whatever. I'm doing this myself, right? I'm finally solving this problem. Okay, so we have the gradient of AX, and therefore the equation of AX is using that like same formula that we had last time. Ugh, that is unreadable. Oh my god. I need to get better with the mouse. Equation of AX is equal to, well, can't say it's equal to. It is just y minus we use the point A here, right? Y minus 1 equals the gradient, which is P minus 1 over 1 minus Q times x minus -1, so x plus 1. So that's the equation of AX. And we usually repeat this for the other three things, right? So can someone tell me what is the gradient of CP? Hey, CP, those are like my initials. I'm waiting here till someone answers. I'm not carrying on. The equation of line CP. Not the equation, the gradient of line CP. Oh, cool. Thank you. Thank you. Yes, yes. So we okay, Isabel says it's q plus one over p minus one. Um yeah, that looks about right, doesn't it? So the difference in yes, okay, thank you very much indeed. The difference in y is, well, we have q at the top and we have minus one at the bottom, right? So that's q plus one is the difference in y. And for the difference in x, you have here you have okay, remember that like when we're doing the difference in, I mean, we're doing like this. Okay, it's a negative slope basically, right? That's what I'm trying to say. So because we took the difference, like the positive difference from P to C, we're taking like the negative difference from like C to P now, right? For the X. So that's one, and then it's one for the X for the C, and then like P as the X coordinate of, well, point P. So it's um like P minus one. That's like the negative one, right? So this does end up being negative overall. So that's good. Um, yeah, that should be good. So therefore you have the coordinate, sorry, the gradient of by to be one over this. So that's just one minus p. Oh, okay, I guess it's I'll do p minus one over sorry. One minus p over q plus one, or one plus q. Therefore, you have the equation of line by is equal to, using point B, 1 minus 1 equals the gradient times x minus 1, using the point 1, 1, which comes from B, right? And okay, I'll just quickly do the last one here. So the equation, or the gradient of dp is difference in y is like, we'll take the positive difference in y. It's the bigger one minus the smaller one, right? That's q minus 1. And then we'll take the smaller one minus the bigger one. That's minus 1 minus p for x. Actually, I don't really like that. I'm gonna rearrange that because I don't like, yeah. Okay, so I'll take the smaller one minus the bigger one for change in y. Um, wait, I'm pretty sure. Never mind. It should have been like this anyway. Sorry, my bad. Um, I think I flipped this sign. This one my sign. yeah. Whoops. Um, okay, never mind. I don't know why I did that. That's fine. And then you have change in x, which is just p minus -1, which is p plus 1. So that's cool. Therefore, the gradient of CZ is -1 over that gradient, which is just p plus 1 over q plus 1. So you have the equation of CZ is using the point C, y minus the y value of C, which is -1, so y plus 1 equals the gradient p plus 1 over q plus 1, and then x minus the x coordinate of C, which is 1. Okay, so we have our three equations now, right? Our three equations are this one, and this one. And you could get a fourth equation as well. It's about necessary. I'm like you could do the same thing where you calculate AP then the gradient of like dw or whatever, and then you get like the fourth line that we're trying to show is concurrent. But it suffices to just show these three are concurrent, right? So we want to find the point like some point which satisfies all three of these equations, i.e. lies on all three of these lines. So what can we do? I mean, obviously we could just like solve simultaneously, right? And you should get an answer if the problem statement holds true and if we didn't make any algebraic mistakes, right? Um yeah, so what's a smart way of doing this now? PQ. Ah, wait, no. PQ. Oh no. Okay. What you notice now is I'm just gonna say by inspection, okay, consider whoops. Okay, consider a new point Q, which we'll define to be the point let's say like negative Q. Wait, what is the solution for this one now? Oh, this is too hard. It's like yeah, okay, I was trying to just guess the answer. Um yeah, unfortunately it doesn't really seem like it's gonna work that way. So let's just I'm just gonna solve this simultaneous equation. Okay, on paper, I'll be right back. You guys probably can come and join me and have fun, right? Yeah, this is the sad truth of coordinate bashing. Sometimes it's not very fun. Like read most of the time, it's not that fun. But yeah. I don't want to do this. What the hell's the answer? Okay. Has anyone gotten anything that maybe looks like something that could resemble possibly an answer? I mean I did get an answer, but this is surely incorrect. Well, I'm about to end the recording and just like do this. Okay, wait. Okay, I got an answer. I got x is 1/p, but that's incorrect because 1/p is clearly outside the square, which I don't think it is. Um, whoops. Okay, wait. Let me recheck the working. Oh god, yeah. This is why I don't do code bashes, right? And I mean, it's not like I wouldn't recommend you doing them. I feel like a lot of the times it's actually no, it's good. It's good. Like if you know you can do it, right? Just do it. It's fine. Um, but yeah. Oh, I missed a negative sign here. Wait. I got it. I got it. Wait, what? Okay, after doing the calculations, I literally got x is equal to negative q. Is that not what I wait? Is that not what I had right at the start? Like when I guessed it, because that's what I thought it was. Um, wait, am I? Oh my God, it's literally just negative qp, isn't it? Yeah. Whoops. Okay. I think I should have been able to just guess that right at the start. Anyway, if you do the algebra, which you know what, I ended up doing the algebra properly. Instead of just guessing it, which is kind of cheaty. Yeah, sometimes you got to just hunker down and do the algebra. You get that all three of these lines concur at some point, like about here, let's say, q, where q is the point negative qp. Um, and if you plug in negative qp into all three of the equations, you'll find that they're all solutions. That's very cool. And if you actually think about this for a second, maybe this can motivate like the actual synthetic solution, which doesn't involve like bashing using like Cartesian coordinates, right? I mean, because the fact is, negative QP compared to like PQ is just the point P. Like if the point P is um at coordinates PQ and point Q is at the coordinates negative QP, uh like what that tells you, I'm pretty sure, is that is just like a 90-degree rotation of P about the origin or something. So yeah, it's kind of interesting, right? What how come they all end up at this rotated point? They all concur at this rotated point. So yeah, the official solution is probably just is meant to just be like rotating the square 9 degrees and having a look at like some stuff, right? But yeah, you don't need to do that. You can just bash it out. Okay, very cool. I think I'm gonna end the lesson there, I guess. You guys are free to go. Cool. Yeah, good luck guys on next Friday or whenever it is. I think it's next Friday. Cool. Bye.